Yeah, oh, thank you for the introduction. So I'm pretty excited today to tell you about some recent work. This is joint work with my collaborator, Rujun Zhang at Fudan University on diagonalizability of quadratic forms. And in particular, the questions that I'll be talking about today are inspired by applications to quadratically constrained quadratic programs, or QCQPs for short. All right, so just to make sure we're all on the same page, a quadratically constrained quadratic program, or a QCQP for short, is an optimization problem in which we're given m quadratic functions, q1 through qm, and each of these is going to be the sum. I'm going to think of it as a sum of a quadratic form induced by some a sub I matrix, a linear form twice b sub I transpose x, and some scalar constant c sub I. Okay, and I guess for the purposes of this talk, the linear and scalar parts are not going to be too important. The main thing to note is that within each quadratic function, there is an embedded quadratic form, which is going to be defined by some symmetric matrix a sub I. Okay, and in this problem, we're asked to minimize the objective function q1 of x, subject to the constraint that the qi of x's, right, the remaining q sub 2 through q sub m, each evaluate to 0. Okay, so why do we care about QCQPs? Well, I claim that they're highly expressive, and this is a very useful property from a modeling perspective. In particular, they're so expressive, in fact, that you can easily capture difficult problems such as max cut, max clique. More generally, you can even capture any binary program or any polynomial optimization problem as a QCQP with only, I guess, a polynomial blow up in the size of the problem. And so I guess, even from this short list of the things you can capture with QCQPs, we immediately see that QCQPs in general are going to be NP hard. Okay, so this is a difficult class of optimization problems. Within this class of QCQPs, however, I claim there's a slightly simpler class that we can think about. This is the class of diagonal QCQPs. Okay, so this is the subclass of QCQPs where each of the quadratic forms, right, each of these a sub I matrices is diagonal. Okay, and concretely, what that means for the quadratic functions, right, the q sub i's, is that if you expand this x transpose a sub I x term, right, the term that captures all of our degree 2 terms, you'll note that we only ever see, these, I guess, monomials of the form xj squared. Right, specifically, we will never see, xj times xj prime for j prime not equal to j. Okay, and so in some sense, people like to call these problems separable. Okay, so before I tell you in what ways they are nicer, I'm going to first qualify the statement a little bit, because they aren't nicer in any broad complexity theoretic sense. I guess we can still capture NP hard problems as diagonal QCQPs. Okay, I guess in particular, binary programming can be easily be rewritten as a diagonal QCQP. Okay, so in what ways are they nicer then? So first, when you have a QCQP in hand, one thing that you might want to do, because the QCQP in general is non-convex, you might look at one of its convex relaxations and try to solve that instead. In this direction, one of the more powerful relaxations we have is the semi-definite program relaxation, or the SDP relaxation for short. In particular, in the setting where your QCQP is diagonal, it has been observed that the SDP relaxation actually corresponds to a second-order Krohn program. Okay, if you don't know what a second-order Krohn program is, that's not too big of a deal, because I won't be talking too much about this in the remainder of the talk. I think the main takeaway is that the second-order Krohn program in general is going to be much more tractable than the semi-definite program. It scales better, especially for large n's and large n's. Okay, and I guess this observation has been made to attempt to solve some, I guess, SDPs, large SDPs in practice. Another way in which they are nicer is that if you are taking this SDP relaxation, then one thing you might ask is this SDP relaxation exact? In some sense, do I lose too much when I take the SDP relaxation of my QCQP? In the setting of a diagonal QCQP, so I guess, while we have in general some sufficient conditions for when a SDP relaxation of a QCQP is exact, the conditions that we have for diagonal QCQPs in particular are much more convincing and stronger. They're more indicative of being, I guess, perhaps the right reason or good sufficient conditions. Okay, and finally, but perhaps most importantly, if you have a QCQP in hand and you're trying to solve this QCQP, then unless you can do something relatively clever, or perhaps your QCQP is really simple, most of the time you're just going to take your QCQP and stick it into a black box global solver. Okay, so one of these could be, for example, Gurobi. And what we've observed is that diagonal QCQPs are handled much more efficiently than their general counterparts in these black box global solvers. Okay, so I guess, given this story so far, you might ask, if I'm looking, if I'm currently looking at a specific instance of a QCQP, can I rewrite it as a diagonal one? Okay, and what do I mean by this? Well, I could reformulate this, I could formalize this question in a couple of ways, but for now, I'm going to think of it as this following problem. I'm going to say, suppose I'm looking at a set of A sub I matrices, right? This is the A1 through AM. These were the quadratic forms in my original QCQP. And I guess they're symmetric matrices. The question is, can I find an invertible P matrix? Right, this is again a square n by n matrix, such that P transpose A sub I P is diagonal for each I simultaneously. Okay, so we only get to pick a single P that needs to diagonalize each of the A sub I matrices simultaneously. And I think one thing to note is that here I'm only requiring P to be invertible. Okay, so this is going to be slightly weaker than, I guess, if you were to require P to be orthogonal, as you might expect from, I guess, like spectral theorem or something like this. Okay, so before I get into too much about what this property is, perhaps I should tell you why we care about this property. Where does this definition come from? So I guess the idea is that suppose this P matrix does exist, right? What can I do with it? Well, supposing that I had this P matrix, what I can do is, instead of trying to optimize my QCQP over the original variable x, I can reparameterize my x space, right, this Rn, with this P times y. Okay, so y is going to be my new parameterization of Rn, okay, via, I guess, this relation. And the nice thing here, right, the reason I guess we're requiring P to be invertible is that when P is invertible, this is going to correspond to a bijection. Okay, so I guess, there is an optimal solution in the X space if and only if there is the same optimal solution when as, parameterized by Y. Okay, so what I can do now is that I guess I can rewrite my quadratic function. So for example, Q sub I, right, recall this was the definition of my quadratic function Q sub I. I can reparameterize it using the Y coordinates. That is to say, each occurrence of X, I'm just going to replace by P times Y. And then I guess rearranging terms, we'll note that the new quadratic form in the Y variable is this diagonal matrix, which by assumption is diagonal. Okay, cool. So I guess this is why this particular formulation might be one way to formalize this question. I'm going to just capture this as a definition for now. I'm going to say that the sets, these A sub I matrices, where this invertible P matrix exists, I'll say that these sets are simultaneously diagonalizable via congruence. Okay, and this congruence property, I guess this word congruence corresponds to the fact that I'm taking P transpose on the left and P on the right. Okay, cool. So now that I've told you a little bit about this, set up a little bit of this background, I can tell you a roadmap for the remainder of the talk. Okay, so I've told you a little bit about QCQPs and why we might want to diagonalize them, and what it means to simultaneously diagonalize a set of matrices. Okay, and then so next I'll tell you a little bit more about this SDC property. Right, so that recall SDC was simultaneously diagonalizable via congruence, and we'll see some first examples. Right, we'll see examples and non-examples of this property. And I'll say that this SDC property is very well understood. We have complete characterizations of it even and like some of these results are folklore. But what I'm going to, I guess the point of this section is not to learn everything there is to know about the SDC property, but rather I'm just going to give you some sufficient conditions or for when a pair of matrices A and B is SDC, okay? The purpose of this is that this will allow us later on to contrast our results. Okay. Next, I'll tell you about some new definitions, some new notions of simultaneous diagonalizability. And in particular, I'll define some property that we call d-restricted SDC. Okay, I'll formally define this, later on in the talk, but for now, you can think of this as being the restriction of SDC sets in higher dimensions to lower dimensions. Okay, in some sense, right, the SDC property is not going to be well behaved under projection. And so, even if you do not have an SDC set in lower dimensions, you might be able to recover it as the projection of an SDC set in higher dimensions. Okay, and if this is a little fuzzy, that's okay. I'll hopefully explain all of this more formally later on. Next, I'll tell you one of our main results in the paper, which asks when a pair of matrices is one RSDC. And that is to say, when is the projection of an SDC set in one additional dimension? And the surprising thing here is that the sufficient condition I will give for you is going to hold almost everywhere. Okay, so in particular, if you, I guess, if you're generating these A and B according to any, nice enough random distribution, you're going to get this one RSDC property with probability 1. Okay, next, I'll tell you about some numerical results that apply our constructions in this one RSDC property to try to solve some QCQPs more efficiently. And then finally, I'll wrap up by telling you about some additional work that I've done in this area, in the same paper but I won't be able to get to in detail today, as well as some future directions inspired by the numerical results. Okay, I'm going to pause here in case there are any questions. Okay, all right, so let's get started on this prior.
I have a question, actually. Yep. Is sort of the long-term goal of all this diagonalization work to, like, as a method for solving? Like, we'll take some SDC that we don't know any fast way to solve, turn it into a diagonal one, and then, or we'll take some quadratic, some QCQP we don't know how to solve, turn it into a diagonal one, throw it into a solver, and hope for the best?
Exactly, yeah.
So sort of the goal is not just that we can diagonalize things, but we can diagonalize things we didn't know how to solve quickly before, and after doing this, now we can solve it quickly.
Yeah, so right, so I think the long-term goal is that if this property, I guess after this work, right, we now know that the one RSDC property, or for example in general, the d-restricted SDC property is much more general than the SDC property, and it allows us to diagonalize instances which we previously did not know how to diagonalize. And I guess the preliminary numerical results, these experiments that I'll show you, show that this can lead to computational speedups.
Great, thanks.
Yep, cool. All right, so I'm going to move on. So just to remind you, the SDC property, right, it says that we need to be able to find this invertible matrix P, which simultaneously diagonalizes all of the A sub i's. And here's just a theorem. This is well known. It's you can find a reference to it, for example, in Horn and Johnson. It's unclear who first recorded this fact. Says that suppose you have an invertible matrix A. Okay, then the pair A and B is SDC, right, simultaneously diagonalizable via congruence, if and only if the matrix A inverse B is diagonalizable and has real spectrum. Okay, so what does this mean? So I guess, recall, I guess A inverse B now is no longer a symmetric matrix, right? You should just think of it as some n by n matrix now. We say that it is diagonalizable if it has a full set of eigenvectors, right? That is to say, it doesn't have any of these, Jordan blocks of dimension greater than or equal to 2. And to say that it has a real spectrum is to say that all of its eigenvalues are real. Okay. I guess the thing here is that even though A inverse P is going to be a real n by n matrix, it can still have complex eigenvalues in the same way that a real polynomial can have complex roots. Okay, and I guess in some sense this diagonalizability is not too big of a deal, this part, I guess you shouldn't worry about too much. The real issue is that the eigenvalues are, often going to be not real. Okay, and I hope that this theorem is not too hard to remember. We will need to use it a few times in this talk, but I will try to remind you of it when we need to. Okay, so this definition and this theorem are probably still a little mysterious. Let's see some examples. So the first example, I'm going to see if anyone can help me with this. I claim that a single matrix, right, A, this is a symmetric matrix, is SDC. Can anyone tell me why?
Spectral theorem.
Cool, perfect. Yeah, exactly. So, spectral theorem tells us that right, there exists some basis under which A is diagonal, right? P, in fact, by spectral theorem, P is going to be an orthogonal matrix. Okay, and I claim that, in fact, this orthogonality, this property, which is, I guess, returned by the spectral theorem, is much stronger than the invertibility that we require. Okay, and I wanted to illustrate this with a second example. So I claim that if A is positive definite, then the pair A and B is always SDC. Okay, and I'll prove this for you in a second. It's not obvious. Perhaps it's obvious from the theorem statement, but I think a priori it's not obvious. But I think the main reason I wanted to show you this example is to emphasize that if you're going into if you're looking at this property and assuming that P is going to be orthogonal, right, as opposed to just simply invertible, then the SDC property, this obviously would never hold. Right, somehow the invertibility is much weaker than orthogonality. What do I mean by this? Right, I guess you can simultaneously diagonalize a pair of matrices A and B via an orthogonal transfer, like an orthogonal congruence, right? If and only if A and B commute, right? On the other hand, right, clearly if A is positive definite, then that's not going to imply that it commutes with any arbitrary matrix B. Okay, let's see now like why this is in fact SDC. And I claim, you need to look at this, matrix here, this A negative half B times A negative half. Right, this is, perhaps for now, we'll just think of this as being pulled out of a hat. I can get into like where this comes from later on, if you want to ask, perhaps at the end of the talk. But I'll just look at this matrix here. This is, again, a symmetric matrix. And so I can apply spectral theorem to this new matrix. Okay, so perhaps, I'll get some U, right? This is my orthogonal basis matrix, such that U transpose this big matrix here times U is, again, a diagonal matrix of eigenvalues. Okay, so lambda here is going to be the eigenvalues of this larger matrix. Then, collecting these two terms, rearranging a little bit, I see that this A negative half times U matrix, diagonalizes the B matrix. Okay, and the thing to note here is that A negative half times U is going to be invertible, right, because A is invertible and U is orthogonal, but it's not going to be necessarily the case that this matrix is orthogonal again. Okay, and now I claim that we're essentially done because in fact A negative half U also diagonalizes the A matrix. How you see this is if you expand and then cancel out the A negative half A negative half term, you're left with U transpose U, which by assumption, right, the spectral theorem tells us that U is going to be orthogonal. So we get the identity matrix. Okay, so this, perhaps is, a little bit mysterious, but I think the main takeaway is just that a pair is that the invertibility criterion is, much weaker than orthogonality. Okay, so we've seen two examples.
Yeah.
Yep.
So you didn't use the previous theorem.
Yep. Yeah, so we could also see that this is SDC using the previous theorem. But I wanted to, as our first example, like real example, I wanted to actually just do it out. How you would see that this pair is SDC using the previous theorem. And perhaps this is a good time to explain like where this matrix comes from, is that we want to understand whether A negative or A inverse B is both diagonalizable and has real spectrum. Okay, well, A inverse B is similar to this matrix, right, by multiplying by A half on the left and A negative half on the right. And in particular, its eigenvalues are going to be the same as the eigenvalues of this matrix. and its eigenvectors are going to be up to change of basis, the eigenvectors of this matrix. Cool. All right, so let's see our first non-example. So this pair of 2x2 matrices, is actually going to come up a few times in this talk. But I claim that A and B are not SDC, right? And how we're going to see this is we're going to apply the previous theorem. And here, we can apply this because A is invertible, right? So we need to check that A is invertible. But once A is invertible, then we know that A and B are SDC if and only if A inverse B is both diagonalizable and has real spectrum. Here, I claim that this matrix is in fact going to be diagonalizable. But if you look at the eigenvalues of A inverse B, that is to say, you look at the roots of the characteristic polynomial of A inverse B, which is, I guess, z squared plus 1, say, then the eigenvalues are going to be plus or minus I, right? This is the imaginary unit I. In particular, we deduce that A and B are not SDC. Okay, cool. So before I tell you, I'm going to move on now, but before I tell you our new definitions, I want to, I guess, recouch the SDC property and maybe a slightly different light, in order for us to be able to contrast and compare our new definitions. So this is not too hard to show. I claim that a set of matrices is SDC if and only if I can find a set of vectors L1 through Ln, which form a basis of Rn. And what I want is that after fixing this basis, I need for each of my A sub I matrices, you need to be able to write it as a linear combination of these outer products, L sub j transpose. Okay, in this format, I guess, in this definition, it's clear that a single matrix is SDC, and perhaps it's a little murky why a pair of matrices should be SDC. But I guess even in general, like if you're given a set of matrices which is not SDC, one question you might ask instead, right? That is to say, you can't find L1 through Ln. What you might ask instead is how many additional vectors do I need? Maybe I'm going to allow myself n plus d vectors, right? L1 through Ln plus d. You might ask, how many do I need so that I can write A and B as a linear combination of these outer products? Okay, and naively, right, if we were to apply spectral theorem, for example, to A to get one set of eigenvectors, and then again to B to get a second set of eigenvectors, naively we could answer, 2n. 2n is obviously sufficient. And as a sneak peek of the remainder of the talk, we'll see in fact that n plus 1 will suffice, almost always.
Alex, if you restrict that basis to be orthonormal, then this becomes the usual regular simultaneously diagonalizable. But here, I guess, more interesting things probably happen when they're not orthonormal.
Right, exactly. Yeah, so this is exactly, that's exactly right. And I think it's a very good point. This is what I was saying about, if we're requiring P to be orthogonal, then that's going to be equivalent to requiring this basis to be an orthonormal basis. And requiring P to be invertible is just to say that L1 through Ln needs to be a basis. Okay, cool. All right, so now I'm going to move on and tell you about some new definitions and some sufficient conditions for this new definition. This is the d-restricted SDC property, or in short, the d-RSDC property. I'll say that a set of matrices A sub I is d-RSDC if for each A sub I can augment it into some bar A sub I matrix. Right, so this is I guess a block matrix now with top left corner A sub I. And after A sub I guess there are D columns to the right and D rows below of junk, right? You can append whatever junk you want beyond this A sub I matrix. And what I want of these augmented bar A sub I matrices is that the set that they form, now this is some subset of Sn plus D, right? This n plus D by n plus D symmetric matrices. I want this larger set, right? This lifted set to be SDC. Okay, so this is some definition, and I'll get back, later, on the next slide, telling you about some sufficient conditions for it. But before we do that, let me just tell you why I care about this property. How am I planning to use it to solve QCQPs? Okay, and I think the first, relatively simple observation is that, the quadratic form induced by A sub I on my x vector is equivalent to the quadratic form induced by this lifted bar a sub I onto the vector, which is x, and then d many zeros below it. Okay, so what I can do is, I can go into my QCQP and replace each of the original x transpose a sub I x's with this new, I guess, rewriting of x transpose a sub I x. And then I can do something relatively superficial, which is to take each of these d-dimensional zeros and replace them with a d-dimensional variable, which I'm going to constrain to be equal to 0. Okay, so not much has changed, but I claim that this is sort of nice, right? Because now the quadratic forms in this new problem are all SDC by assumption, right? By this definition. So in a sense, what I'm doing is I'm lifting my original QCQP, which was not diagonalizable, into a QCQP which is diagonalizable. And then after doing this lifting, I can then do my change of basis to get a diagonal QCQP. Okay, so I guess this is a sense of why I care about this d-RSDC property. But now, let's see that in fact this actually does hold for these pairs of matrices. Right, this is the fact that I was telling you guys about earlier. So just to contrast against the SDC property, what is the difference? Is that I claim that this actually captures this question that I was asking earlier. This is a little trickier to show. Is that a set of matrices is d-RSDC if and only if I can find these n plus d vectors in Rn. Now, it doesn't really make sense to require this set of vectors to be a basis. This is never going to hold if d is greater than or equal to 1. But I can still require that they span Rn. Okay, and what I want of this set of spanning vectors, I guess, is that each A sub I matrix needs to be the linear combination of the outer products, L sub j transpose. Right, so this, other than this plus d and this basis to spanning, this is the original SDC definition. Okay, and what we observed earlier is that any pair is naively n-RSDC. But I guess this theorem that we proved says that if you give us any pair of matrices A and B, satisfying some assumption that I'll talk about in just a second, then this pair is 1 RSDC. Okay, so what is this assumption? Let's, a few words are in order about it. This assumption says, first of all, I need that A is invertible. Okay, and after assuming that A is invertible, I furthermore need that A inverse B, right, this matrix, has only simple eigenvalues. Okay, so recall that I guess we say an eigenvalue is simple if it is not repeated, right? So all of the eigenvalues are distinct, right? I guess it's equivalent, it's very similar to saying, if you have a polynomial and you're looking at its roots, that none of the roots are repeated. Okay, and I guess the main takeaway here, if this is slightly unfamiliar, is just that A inverse B, is with probability 1 going to exist, or I guess the set of the set of pairs for which A inverse does not exist, is the solution to some polynomial, and it has measure 0. And similarly, you can show that the set of pairs where A inverse B has repeated roots, repeated eigenvalues, is also going to be a set of measure 0. Okay, and in particular, if you're generating A and B according to any, I guess, continuous random distribution, or alternatively, if even if A and B are given adversarially, but you're allowed to perturb by arbitrarily small amounts, then you can, without rationality, assume that this exists, that this property holds. Okay, so ideally, I would love to be able to tell you about the entire proof, but I will only be able to tell you, bits and pieces of it today. But perhaps the first step, and maybe a kind of cool tool that hopefully one of you will eventually be able to use, that I found, is this canonical form for pairs of symmetric matrices. Okay, so I guess what is this? So I guess similar to the way that Jordan canonical form tells you that if you're trying to prove a fact about some linear operator which is basis invariant, then you might as well prove it, you might as well work over the basis in which your matrix is block diagonal with nice blocks. Okay, you have a very explicit, you can very explicitly write down what your matrix is in this basis. Similarly, like here, what this result says is that if you're trying to prove a fact about a pair of symmetric matrices, which is basis invariant, then you might as well work over some particular basis under which A and B are simultaneously block diagonalizable. Right, they both have the same block diagonal structure, and in each block, in each diagonal block, they will have a very specific canonical form. Okay, they will even look quite a bit like these Jordan canonical blocks. Okay, so I'm going to do the rest of the proof, assuming that I've done this transformation, and in fact, instead of looking at an arbitrary pair of block diagonal matrices with an arbitrary number of blocks, I'm just going to look at a block diagonal matrix with a single block, right? So I guess in some sense, this is not a block diagonal matrix at all. But we're going to see that it's going to be this pair of matrices A and B again. But I guess the thing to note here is that in fact, this is what your canonical blocks are going to look like. Right, so this is in fact quite indicative of the general situation, and the computations I'm about to show you do generalize quite easily to arbitrary pairs of symmetric matrices in their canonical forms. Okay, so just to recap, what are we trying to do here? Right, so we have this pair A and B, which we saw previously was not SDC. Right, it had A inverse B had eigenvalues plus or minus I. And what we're trying to do is we're trying to find an augmentation, bar A and bar B. Right? We're going to try to stick some scalar values into each of these start entries, such that bar A and bar B are now, these augmented versions are SDC. And how I'm going to certify this is I'm going to use, the previous theorem, the folklore theorem, that says that if bar A is invertible, then this pair is SDC if and only if bar A inverse bar B is diagonalizable and has real spectrum. Right, so I'm going to try to get to a pair of matrices that satisfies this condition. Now, this diagonalizability is a little finicky. So I'm going to replace this diagonalizability with the assumption that bar A inverse bar B has simple eigenvalues. Right, so now I want it to have real simple eigenvalues. And I guess the way you should parse this is that I want it to have real eigenvalues which are all simple. Right, this is, I guess, I'm not saying it needs to be easily understandable or something like that. Right, so I guess the fact that I'm using here is that if a matrix has simple eigenvalues, then it is automatically diagonalizable. Okay, so finally, this bar A, because I'm working with its inverse, I'm going to try to construct this bar A in such a way that it's easy to take its inverse. So the one thing you might try to do is you could just zero out this top right and bottom left blocks and stick a single 1 here, right? And conveniently, this was really just a design decision, but conveniently, this bar A matrix is going to also be its own inverse. This is not, too important. It's just a convenient fact. Okay, but now that we've, parameterized bar A this way, we've, given up a bunch of degrees of freedom, I'm going to probably need to do all of my heavy lifting with this bar B matrix, right? I'm going to fully parameterize all of the, degrees of freedom that I have in bar B. Okay, and I guess, the reason that these alphas are the same and these betas are the same is because I still need to satisfy that bar B is a symmetric matrix. Okay, so, we have this bar A and bar B, and we want to understand what are its eigenvalues. That is to say, what are the roots of its characteristic polynomial? In if I'm writing it as a polynomial in Z, I guess it's going to be a polynomial in Z with coefficients which are functions of alpha, beta, and gamma. Okay, so you can write this out and collect terms, perhaps cleverly, and this is one way that I decided to collect terms. But why did I think that this was a good way to do it? I think the reason is that there are going to be two observations. First, if we look at these blue polynomials, right, the z squared plus 1, z and 1, these polynomials actually form a basis for the degree 2 polynomials over z, in Z. Right, so recall that degree 2 polynomials in Z as a vector space are a 3-dimensional vector space, and this is going to be one of its bases. This is going to form a basis for it. I guess the reason that z squared plus 1 shows up here is because z squared plus 1, recall, is actually the characteristic polynomial of A inverse B. Right? And so in general, you'll also see, one of these polynomials is going to be the original characteristic polynomial. Okay, the second observation here is that the coefficients in front of these polynomials, right, gamma twice alpha beta and beta squared minus alpha squared, we can think of as, I guess, a three-dimensional vector. Right? It's going to be, first coordinate is gamma, second coordinate is twice alpha beta, and third coordinate is beta squared minus alpha squared. And the function which maps alpha, beta, and gamma onto this vector is going to be a surjective function. Right? For any coefficient that you would like for me to stick in front of these blue polynomials, I can find some alpha, beta, and gamma that achieves those coefficients. Okay, and now I claim we're essentially done because, in fact, whatever I claim, surprisingly, whatever eigenvalues, lambda 1, lambda 2, and lambda 3, you would like me to set for bar A inverse bar B, I can find some alpha, beta, and gamma that satisfies, that has those prescribed eigenvalues. Okay, so this is perhaps a little unexpected, but I guess I'll show you how we're going to do that. But for concreteness, I'm going to assume that lambda 1, lambda 2, and lambda 3 are -1, 0, and 1. In general, you can do the remainder of the calculation I'm going to show you with any arbitrary set of 3 distinct points. Okay, so I guess first, what does it mean for lambda 1 to be an eigenvalue of bar A inverse bar B, right? What is this going to impose on my alpha, beta, and gamma? Okay, so this constraint, all right, is, I guess, is going to be equivalent to saying that lambda 1, or that this characteristic polynomial evaluates to 0 at z equals lambda 1. So I can just write that out, right? Replacing these z's with lambda 1 and I guess moving the z times z squared plus 1 over to the right-hand side. And I guess, now that lambda 1 is fixed to be -1, I can, just evaluate what these blue terms and this term on the right-hand side are. And I'll note that this actually imposes a linear constraint on the coefficients. Okay, I guess the coefficients are gamma twice alpha beta and beta squared minus alpha squared. Okay, and I can collect, the same linear constraints that I would get for lambda 2 and lambda 3 as well. And rewriting this, collecting all of these linear constraints, I'll get this system. Okay, it's a linear system in, I guess, the coefficients gamma twice alpha beta and beta squared minus alpha squared. Okay, and I guess, the lambda 1 equation is just this first row times, I guess, this column vector is equal to -2. Right, and similarly, that's, I guess, these other rows are, I get them similarly. Okay, so now we're going to use the two facts that we saw earlier, right? So we saw first that z squared plus 1, z, and 1 were a basis for the degree 2 polynomials. That in fact tells us that this matrix here is invertible, right? Why? This is akin to saying that if you, choose any y value at lambda 1 and any y value at lambda 2 and lambda 3, I can find some degree 2 polynomial which hits those values. Right, so this is like polynomial interpolation. This tells us that this matrix is invertible, which is to say that there exists some vector I can put here, which satisfies all of these equations simultaneously. Then using the fact that alpha, the map which sends alpha, beta, and gamma to this vector is surjective, I can then, pull out some alpha, beta, and gamma. Okay, and I won't do that calculation for you, but I guess here, this setting of alpha, beta, and gamma is one of these magic settings. Okay, so just to recap quickly, I picked this alpha, beta, and gamma, according to this rule, and forming this bar B matrix, right? This is a matrix that has B in its top left corner and then alpha, beta, and gamma on its, I guess, right and bottom. I now have a these lifted matrices bar A and bar B, such that bar A inverse bar B evaluates to 0, the characteristic polynomial of bar A inverse bar B evaluates to 0 at each of -1, 0, and 1, which is to say that bar A inverse bar B has the eigenvalues -1, 0, and 1, which, by construction are both real and simple. Okay, and then, now just applying the theorem from folklore, we have that bar A and bar B are an SDC pair. Okay, and even though the calculations I was doing for you today were for very simple 2x2 matrices, many of the same calculations generalize almost exactly to, I guess, almost every pair A and B. The only place where I'm using the fact that it has that A inverse B has simple eigenvalues is in this one step here, in which I need to argue that these polynomials form a basis, right? And somehow that's going to be tied to whether or not the eigenvalues of A inverse B are simple. Okay, so now I'm going to move on to some numerical experiments where we try to apply some of this one RSDC construction, which I just showed to you. Okay, so we're going to generate some random QCQPs of this form. Okay, so I'm going to try to minimize some quadratic form, x transpose a sub 1x, subject to the constraint that x transpose a sub 2x is non-positive. Furthermore, I'm going to require x to live in some polytope. Okay, so I guess how am I going to generate these this problem data? So first, A1 and A2, we're going to generate them randomly in canonical form, and then rotate them after the fact. Right. So this canonical, the theorem, this canonical form tells us that for any pair of matrices, there exists a rotation for which after this rotation they're in a canonical form. I'm just going to do that like in reverse. I'm going to first generate them in canonical form and then rotate after I have them in canonical form. Okay, why do I do this? Well, the main reason is that we want access to this parameter k. Right? We want to be able to control k, which corresponds to the number of pairs of complex eigenvalues of A1 inverse A2. Okay, in some sense, you can think of this, abstractly as being how far, as some measure for how far A1 and A2, this pair, is being from SDC. Okay, I guess perhaps an observation here is that when k is equal to 0, right, when A1 inverse A2 does not have any pairs of complex eigenvalues, then up to this like slight minor diagonalizability criteria, A1 and A2 are actually going to be SDC. Okay, and so I guess this k parameter also shows up naturally in all of our constructions. So we thought it would be interesting to measure how the performance behaves as k varies. Okay, and what we did was we generated these random instances, and first we fed the random instance as is into GROB. Next, we performed this one RSDC construction. That is to say, we introduced one new variable with the problem data suitably modified according to our one RSDC construction, and then we diagonalized the instance, and we fed the diagonalized instance into GROB. One thing I haven't mentioned so far, but I think is relatively straightforward, is that if an instance is d-RSDC, then it is also d prime RSDC for any d prime larger than d. Right, so if it's one RSDC, then it's also two RSDC. But I guess this 2RSDC algorithm is going to use a different construction. Okay, so we came up with a different construction that shows that also, I guess, any pair of matrices up to this minor assumption is 2RSDC. And finally, we tested the naive n-RSDC algorithm. Right, this is the algorithm in which we apply the spectral theorem twice, once to A1 and once to A2, and introduce n new variables. Right, just to make sure we're all on the same page. Right, the as-is algorithm is a problem, is a QCQP in n variables, and then we have n plus 1 variables, n plus 2 variables versus 2n variables. Okay, cool. So here are the numerical results for n equals 15. What does this chart tell us? I guess we generated 10 random instances at each of k equals 0, k equals 1, k equals 2, and k equals 3. And for each instance, we fed that instance into each of the 4 algorithms with a timeout of 10 minutes. Okay, so if at 10 minutes, an algorithm hasn't already found an optimal solution, it will return just some objective value. Okay, and for each of those instances, we're going to assign a point, award a point to the algorithm that returns optimality fastest. Okay, so at k equals 0, right, 5 of the instances were solved most quickly by the 1RSDC algorithm, and 5 were solved most quickly with a 2RSDC algorithm. Right, the same story holds at k equals 1, But then things start to get a little funky. So what happens at k equals 2 is that 6 of the instances are solved most quickly with a 2-RSDC algorithm. 1 is solved most quickly with the n-RSDC algorithm. And then there were additional 3 instances for which none of the algorithms managed to terminate before the 10 minutes of allotted time. Of those 3 instances, 1 was solved to the best value with a 2-RSDC algorithm, and 2 more were solved to the best value with the n-RSDC algorithm. Okay, and then when we get to k equals 3, most of the instances were not solved within the 10 minutes of allotted time. But of those instances, I guess the n-RSDC algorithm seems to perform the best if we're just looking at which algorithm returns the best objective value. So what is going on? Well, I guess there are a few takeaways. First is that one of the RSDC algorithms I guess we observed to outperform the as-is algorithm on every test instance. Okay, so somehow diagonalization is helping, at least in some form. Okay, but okay, so maybe I should try to explain what is happening for these larger values of k. Right, going into this these experiments, I was expecting for like 1-RSDC and 2-RSDC algorithms to completely outperform the n-RSDC algorithms. Okay, so what is happening is that as k increases, right, these constructions that we're doing require inverting larger and larger matrices, which are themselves like ill-conditioned. Okay, and in particular, after doing this lifting, right, after doing the lifting, we have to diagonalize the matrices, right? So there's going to be some P matrix associated with each algorithm on each instance. And those P matrices we've observed have condition numbers which blow up with k, right? The condition number of a matrix, recall, is just the product of the norms of it and its inverse. Okay, and in some sense, it measures, how I guess well-behaved your change of basis is. And the numbers we were seeing, are pretty bad, right? When, for example, at k equals 3, the 1-RSDC algorithm, this construction that we have returns instances for which the P matrices, the change of basis matrices, have condition number on the order of 10 to the 3. Okay, the 2-RSDC algorithm was returning instances, diagonalizable instances with P matrices on the order, with condition numbers on the order of 10 squared. And I guess the n-RSDC algorithm, because it's returning an orthogonal matrix, is always going to have condition number 1. Okay, so what we believe and what we saw also for larger k's is that as k increases, the condition number of the 1-RSDC construction that we have, as well as the 2-RSDC construction that we have, mean that it no longer outperforms the naive n-RSDC construction. But the 1-RSDC and the 2-RSDC algorithms do outperform the n-RSDC algorithm at smaller values of k. Okay, so I'm going to wrap up now by just recapping what I told you about in this talk, as well as some additional work in this area, and I'm going to revisit again the experiments and I think what they tell us about future directions. Okay, so in this talk I told you about this d-restricted SDC property. And I showed you, I showed you some parts of the proof of the fact that this 1-RSDC property holds almost everywhere for pairs of symmetric matrices. Some additional results that we have that you can find in the paper are that first, we also define a separate notion, which we call the almost SDC property. All right, so I guess in some sense, instead of this d-RSDC property says that we're going to look for SDC sets in higher dimensions. Okay, the almost SDC property says, instead of looking in higher dimensions, I'm going to look in the same dimension, but I'm going to allow myself to perturb my matrices. Okay, so it's some sort of, I guess you can think of this as a perturbation definition and this as a lifting type of definition. We give a complete characterization of the AST, of the ASDC property for pairs of matrices. And you can find additional results, which are, include some necessary conditions, some sufficient conditions, as well as some necessary and sufficient conditions for both of these properties. In particular, all of our results are for some small number of matrices, right? So for example, we have some positive results for 2 and 3 matrices, and we have negative results that begin to kick in for example, at 7 matrices. Okay, so returning to the experiments, I think it tells us some interesting things about future directions. I think first it tells us that diagonalizability is worth studying in some form, but perhaps right now we don't have the right definitions. Right? Somehow, what the experiments are telling us are that diagonalizability is perhaps a good property, but we also do need to take into account the condition numbers of these change of basis matrices. Right? In particular, it might be interesting to consider a definition of SDC which takes into account the condition number. A different take on this is that, as we saw, right, the 2-RSDC condition number was much smaller than the 1-RSD condition number. Right? The reason for this is that when you have more and more variables, the constructions that you're, the constructions that you can make, you have more and more freedom, and hopefully you can, if you're clever, you can, you can make these condition numbers smaller. And that is indeed what we saw for 2-RSDC versus 1-RSDC. Unfortunately, we don't have constructions, between 1, 2, and n. So it might be interesting to ask whether you can find parameterized constructions that work for any number d between 1, 2, and n. I think this would be interesting because once you have such a parameterized family of constructions, then you can begin asking questions such as, what is the optimal trade-off between condition number and dimension? Okay, so I'll stop here and I'll take questions now. Thanks for coming to this talk.
So Alex, about your construction of the 1-RSDC, where you, so were you using the, so you were using the construction procedure that you indicated on the sort of first, or in the sort of sketch where you said, oh, I'm going to place a 1 in the, on the diagonal, and then that's going to move all the work to B and stuff like that.
Yep.
So is there room to play out there? Like if you chose a different thing to do on A, could you get a better condition number out of that?
Yeah, okay, so yeah, let me move back to these slides. Right, okay, so I guess the short answer is probably, right? There's a bunch of design decisions that I made. First, right, I decided to stick a 1 here and not use any of these variables, which we probably could use and would probably help. Second, right, when you, right, so there's some room for improvement possibly here. Next is that, we have to pick some choice of eigenvalues, right? And your choice of eigenvalues will also, change the lifting that you do and subsequently will cause the condition number to change. And I guess, there are a bunch of variables that you could play around with to see if you can bring down the condition number. But I guess the main difficulty in doing this is that, this construction tells you what the bar A matrix and the bar B matrix are going to be. But the condition number of the P matrix, which diagonalizes these matrices, it's hard to understand in terms of A and B, or bar A and bar B individually. Yeah, I think, I was playing around with the code and just trying, what are, different eigenvalues would do to the condition number, and it just doesn't seem very well behaved. Yeah, so there might be something smart you can do, but I don't see it at the moment.
Does it matter at all that one of your eigenvalues is 0 so that A inverse B has a kernel?
Yeah, so I guess when you say doesn't matter, do you mean about the condition number?
Yes.
Yeah, so it's unclear. I think one perhaps mysterious thing that I was noticing in the code is that I guess in the code we're currently doing like evenly spaced points in between the interval -1 and 1. Right, that was just some decision we made, and in order to improve the code, I was trying to shift these values up and down, as well as scale them up and down. And I think if I recall correctly, scaling does not, or scaling does affect the condition number, but translating does not, for whatever reason. or it might be the other way around, I forget. But if it is the translating, which doesn't affect the the condition number, then perhaps, you know, whether or not you have a 0 probably doesn't matter.
Yeah.
Yeah, but I can double check that experiment and get back to you.
And in the lower matrix analysis that you're doing, I'm not sure why you mentioned the top of the column on the right-hand side of the equality z times z squared plus 1. That's supposed to signify the value of that particular polynomial?
Right. Okay. Yeah. So okay. So let me try to answer. I'm not sure if I got the exact question, but maybe this answers part of it. Is that this matrix here on the left? I'm indexing by, you know, lambda i's. Right? These are the prescribed eigenvalues and these polynomials, and each entry is the evaluation of the blue polynomial at the pink point. Okay. Similarly, on the right-hand side, right, I'm evaluating the polynomial z times z squared plus 1 at the points lambda 1, lambda 2, and lambda 3. Does that?
Yes, that answers it. Okay.
Okay. Cool.
I see. So, Alex, maybe to make sure I understood this question. So, what do we understand about the sort of complexity of this question? Minimize the sort of get the best, minimize the condition number subject to doing this.
Yeah. Yeah. So I guess this is. You know, I tried to look into this. I have to say this is beyond my wheelhouse. I think, you know, folks in numerical linear algebra could probably answer this better. Yeah, I'm honestly, it seems, you know, quite mysterious to me, and the brief experiments that I've run seem to indicate that it's, you know, pretty wild. Yeah, it's like, it's not monotone. It, you know, I figured, you know, either translations don't affect it, or scaling doesn't affect it, but the other one does, and yeah, something like that. Yeah, I think, you know, part of the issue is that I guess where K shows up is that this matrix is going to be a 2K plus 1 dimensional matrix, and each of these, I guess there are these special matrices called Cauchy matrices, or Cauchy matrices, which are known to be, you know, highly ill-conditioned. And embedded within these matrices that we're trying to invert, there are two separate Cauchy matrices. Yeah, I have to say I don't really understand this too much, but I think there are numerical issues that cause it to go haywire for large values of K.
Nice. Cool. Thank you.
Alex, I have a quick question. So regarding the way that you are evaluating the performance, I was just wondering if this is the right way to evaluate the performance or not. So right now you are just thinking the impact of these reformulations of the problem on a particular solver. And, you know, solvers have their own different set of operations, and they may, because of those different operations that they do, they may behave completely differently, unexpectedly.
Yeah. I guess, you know, we could have been more thorough and, you know, tested a bunch of different solvers, but I guess.
No, that's not what I mean, actually.
Okay.
Like, testing a bunch of solvers will just give you a bunch of results, possibly even conflicting. But
Sure.
I was just wondering if there could be a different way to measure, like, whether one reformulation is better than another.
Yeah.
Like, you know, clear comparison things seem to me, the condition number apparently is important, something that you need to think about. And then the number of, like, the lifting that you do clearly is also important.
Yeah.
But, you know, what could be other measures that you may be?
Oh, I see what you're saying. You're saying, like, let's, like, can we get away from running experiments at all, or not experiments, but like plugging things into global solvers, and maybe
tie
we just
this to solver specific things. Like, is there a better way to measure how a reformulation could be better than another?
Yeah, that's a good question. I mean, I guess, you know, if the end goal is to eventually stick this into some solver, then you are trying to, you know, I guess maybe the right thing to do is try to measure some quantities, perhaps better understood than like the solver's performance, that should, correlate well with the solver's performance.
I mean, condition
I
number
guess it's
clearly is one related thing, but
yeah.
What other ways can we measure, like in terms of, I mean, this is one type of lifting, obviously, but in terms of lifted formulations, for example, it's not always, there are results that say that if you lift a little more, then you have a better representation of your problem and it will be much easier to solve than trying to minimize the additional dimension that you're adding. And I mean, with these things, I wonder if there is such a trade-off going on as well.
Yeah. So I think, it'd be interesting to see what other metrics, I guess, we should be evaluating these reformulations on. I guess one thing is that like the size of the reformulation, I guess if you're just measuring size crudely as like the number of constraints, etc., is going to be just the original number of constraints plus d constraints for these zeros. But yeah, I guess somehow, I guess the answer is I'm not sure what other metrics there are, but yeah, they could all be interesting.
Oh, there's another question.
Yeah. Okay. Let me think for a second. Okay, so right. Yeah. Okay. So this is actually something that I didn't mention, but maybe is good to mention because I think it shows that the 1RSDC property is actually quite surprising and special. So I guess the question was whether or not if you take K GOE matrices, whether or not they're going to be K-RSDC. And I think the answer probably is no, because once you move beyond a single a pair of matrices, once you move to 3 matrices, you get some weird behavior. I actually have some slides for this. So right, okay, so suppose we're working over the reals. This is the real version of the statement. This is the complex version of the statement. We can construct for you a set of 7 matrices. Oh wait, sorry. This is the wrong result that I was trying to pull up. This is the result I'm trying to pull up. Right. So we can find, if A is just the identity matrix, right? Say A is the identity matrix, and B and C are generated randomly. Okay, like let's say according to the GOE. Then the rank of the commutator B and C is with high probability going to be 1. Or sorry, not 1. That's going to be full dimensional, right? It's going to be n. So what this theorem says is that if you consider the set of matrices, which is the identity matrix, and then your 2 random GOE matrices, then with high probability, they're not going to be n over 2 RSDC even, right? Not like, so the minimum number of dimensions that you need to lift could vary linearly. Oh, sorry, this is a typo. This should be strictly less than. Yeah, this should be strictly less than.
I see. So this is basically means even 3 matrices can be like n by 2 RSDC.
Yeah, and specifically not n over 2 minus 1 RSDC.
I see.
Yeah. So I think this shows that the 1 RSDC property is very special to pairs of matrices. Yeah, it's very special to pairs of matrices and is unlikely to increase at a small amount or to be a small number like when you're beyond pairs of matrices.
But I remember you said in the beginning that you're trying to diagonalize all the matrices you have in your system.
Yeah.
So,
yeah. So
does that not work for more than 2?
Right. So I guess this RSDC property. If you have d-restricted RSDC property, then you can diagonalize by adding just d additional variables. In the case where you only have 2 quadratic forms to worry about, right? So for example, in the setup of the experiments, right, we had 2 quadratic forms, and then the rest of the constraints are all linear. Then we can perform this one RSDC construction. And then you might ask, does this property hold? Let's say, does one RSDC hold for 3 matrices? And the answer, or this theorem, this construction, or this counterexample shows you that it can't hold for small values of D if B and C have have a large rank commutator, and it says that this RSDC property. If you apply this construction that is guaranteed by the RSDC or d-RSDC property, it might lead to many additional dimensions. Right. I guess the thing to compare here is that if you are applying spectral theorem naively, right, then you might expect 3n, and this says you can potentially this rolls out smaller than 1.5n.
I had a quick question about canonical forms of pairs of symmetric matrices that you mentioned.
Mm-hmm.
What do you mean canonical in that sense? So any 2 symmetric matrices can somehow be reduced to this canonical form?
Yeah, exactly. So there is, this canonical form. It says that if you give me any pair of symmetric matrices, then I can find some change of basis, right? It's going to be, similar to the congruence transformation that I mentioned previously, such that after this congruence transformation, A and B are both block diagonal, and in each block, there are each of the blocks can be one of, I guess, 4 types, right? There are multiple types of blocks. I guess perhaps it might not make sense to try to explain this right now. I guess the main takeaway is that there is a canonical form for what these pairs of symmetric matrices look like.
I think, and each block is 2 by 2 or n by n?
Yeah, so each block is can be either it can be any size. The blocks that so I guess the blocks, each block is going to correspond to an eigenvalue of A inverse B. Okay, and if the eigenvalue of A inverse B is real, then the block can be any integer sized. If the block is a complex, corresponds to a complex eigenvalue of A inverse B, then the corresponding block needs to be an even number. Right? This is somehow related to pairs of roots coming up.
I see. This is quite interesting. And A and B in those papers are defined over the field of reals.
Yeah. Oh, okay. So yeah. So let me see. Let me see where I mentioned it. So Ulig, I think, does the real setting. You can, if you find Lancaster and Rodman, it also does the complex setting.
I see.
Complex Hermitian forms over the complex numbers. And I guess part of their exposition, I think, is slightly more complicated than necessary because they consider arbitrary pairs A and B, whereas for our purposes, it suffices to pick right, like the RSDC property or the SCC property. Any of these properties that I was considering today are properties of the subspaces generated by the pairs of matrices.
Yeah, so you can kill away things that are in the kernel.
Yeah. You
can make the rank maximum or something. Yeah. Okay.
Exactly. Right. So I can pick a maximum rank element and then work with that.
Right. Okay. Okay. Thanks a lot.
Yep.